Hi everyone, welcome back to Deviations. In today's video, single variable calculus, we will be dealing with indeterminate forms. Now this is one of my favorite topics that we're going to be covering in this course because it really shows how the derivative is going to help us firsthand with solving some pretty important problems that are really foundational to the idea of calculus. So we are going to be doing a fairly good amount of differentiation in this video, so I recommend that you watch my previous videos to brush up on that. However, we won't be dealing much with maxima and minima or graph sketching today, so if you haven't seen those videos, that's fine. So we're going to get started with some indeterminate forms. Now, these are some really important things that we're going to be talking about today, and it's going to be a little bit theory heavy, but we should be able to get through it together. So we're going to start off with the problem. So the problem is that we have some indeterminate forms, and an indeterminate form is when we have a limit but it could evaluate to something like 0 over 0. Now in the past in Unit 1 when we were talking about limits, that meant that we could usually use some manipulation, algebraic or trigonometric, what have you, and that would allow us to solve the limit by simplifying it, maybe changing some functions around. And that would allow us to evaluate the limit to an answer that we could get. So this indeterminate form, which could be 0 over 0 or infinity over infinity, usually means that we can do a little bit more. So sometimes we can do that trigonometric and algebraic manipulation to evaluate, but sometimes we can't, and a result won't be yielded. So today we are going to be talking about some tools that we can use to make these limits that we might not have been able to evaluate a little bit more possible, or completely possible in most circumstances. So the rule that we are going to be discussing today is called L'Hopital's rule, and this is, again, a foundational rule that you should definitely write down. It's very important for solving limits, and you will definitely be seeing it again. Now, L'Hopital's rule says that given a function f of g, f and g that are differentiable, and the derivative of g is not 0 because that's going to be in a fraction, we don't want to divide by 0, on an interval I that contains a point a, or a value a. Suppose that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0. Or likewise, the limit as x approaches a of f of x is plus or minus infinity, and the limit as x approaches a of g of x is plus or minus infinity. So again, this yields, if we put it into a fraction, which is what we are going to do, f of x over g of x, then we do the limit, that's going to be 0 over, so there we are going to get, we're going to get 0 over 0 for the first limit, and then infinity over infinity for the second one, and of course that is an indeterminate form. Alright, so what can we do? That means that if I want to evaluate the limit as x approaches a of f of x over g of x, I can rewrite that as the limit as x approaches a of the derivatives. So the limit as x approaches a of f prime of x over g prime of x. So if I can take the derivative of both functions really easily, I just plop them in there, and I might be able to yield a result. What's great about L'Hopital's rule is it's like the product rule, the chain rule. You can apply it multiple times. So we can apply this rule as many times as we need to, although it would probably be wise to do some manipulation in between just so that we're not going in circles and applying it as many times as we can. And you might be seeing a quotient here, and that's what L'Hopital's rule mostly deals with. But again, we can deal with products as well. So we can just manipulate our functions so that they can be put in that fraction form, and then we can differentiate that, and that will allow us to use L'Hopital's rule in the same way. And of course this works with all of the other operations as well. We can manipulate them so that they're more favorable to work in that quotient situation that we have in L'Hopital's rule. Okay, so I've been doing a lot of abstract talking here, so why don't we deal with some examples? So our first example is going to be fairly easy. We're just going to be getting a feel for L'Hopital's rule as a whole. and we are going to take the limit as x approaches 1 of the natural logarithm of x over x minus 1. Okay, so first what we are going to do is we are going to confirm that this limit is going to be indeterminate. Now the limit as x approaches 1 of the natural logarithm of x is 0. Again, we have that intercept there. And then the limit as x approaches 1 of x minus 1 is 0. We can apply direct substitution into both of these, and they will both yield 0. And if I want to plug them back into the fraction, that's going to yield 0 over 0, which of course is indeterminate. So we have confirmed that our limit is indeterminate. So what we will do now is we will differentiate both of our functions, the top and the bottom, and then we will put that into L'Hopital's rule. So if I differentiate the natural logarithm of x, I'm going to get 1 over x. That's a elementary derivative there, and of course the second one is as well. If I differentiate x minus 1, of course I just get 1, as we have that power reduction going on there. Okay, so now let's plug this back into our limit. So I'm going to take the limit as x approaches 1 of 1 over x over 1. And that will be the same as the limit as x approaches 1 of 1 over x. And of course, if I plug in 1 as x, that is going to be 1. So I've evaluated the limit, and we've used L'Hopital's rule successfully to yield an answer of 1. So let's do another example. So we are going to take the limit as x approaches 0 of the tangent of x minus x over x cubed. Of course, we are going to have an indeterminate form here. Okay, so we have confirmed it is indeterminate. Now what we will do is, of course, we are going to differentiate the functions. So if I differentiate tangent of x minus x, we're going to get secant squared of x minus 1. Of course, that requires that you know the derivative of the tangent of x and the derivative of minus x, of course, secant squared x minus 1. If I differentiate x cubed, that's a monomial that has the power reduction, and it goes to 3x squared. So now we can rewrite this as the limit as x approaches 0 of secant squared of x minus 1 over 3x squared. Now, the secant squared of 0 is going to be 1, and if I subtract that by 1, that's 0. And of course, 3 times 0 squared is 0 as well. So we have an indeterminate form again. All right, so of course, this is fine. We just need to apply L'Hopital's rule again. So if I apply L'Hopital's rule again, I'm going to differentiate the top and the bottom. So if I differentiate the top, I need to differentiate secant squared of x minus 1. And if I do that, I'm going to get 2 times the secant squared of x times the tangent of x. Okay, now if I differentiate 3x squared, of course, another monomial, that will give us 6x. And now we can plug that into the limit. So we're going to get the limit as x approaches 0 of 2 secant squared x tangent x over 6x. Now, even though the secant squared of x is 1, secant squared of 0 is 1, the tangent of x, the tangent of 0 is 0, and 6 times 0 is 0, so that kills the whole limit. So that's going to be 0 over 0. So again, we have an indeterminate form. Now I'm going to take the opportunity to do a little bit of algebraic and trigonometric manipulation, just so that when we apply L'Hopital's rule again, we might yield a better result. So again, this is just showing that even though I can apply L'Hopital's rule as many times as I want, it's a good idea to do some manipulation in between, just to make sure that we are going to be doing this in the most efficient way possible. So if I have the limit as x approaches 0 of 2 secant squared x tangent x over 6x, I can rewrite this as 1/3 times the limit as x approaches 0 of secant squared x times the limit as x approaches 0 of tangent x over x. Now, of course, the limit as x approaches 0 of secant squared of x times 1/3 is just going to be 1/3, and then I'm going to be multiplying that by the limit as x approaches 0 of the tangent of x over x. Okay, so finally, we are going to do just a little bit more. We're going to apply L'Hopital's rule one more time. We're going to differentiate tangent x over x. So if I differentiate tangent x, I get secant squared x, and if I differentiate x, I get 1. So that leaves us with 1/3 times the limit as x approaches 0 of the secant squared of x over 1, which, of course, is 1/3. So even though we needed to apply L'Hopital's rule 3 times in this example, we still got our answer. So again, it's a great rule that we have. This limit, back in Unit 1, we would have been thinking, I do not know how to solve that, but now we do, thanks to L'Hopital's rule and our knowledge of the derivative. Thank you for watching today's video on L'Hopital's rule and